Hey, Evan, I thought I would try to run through this solution again. We got kind of shortchanged on it. And so I thought, I know. I got a little bit of extra time. I'll make you a quick video and anybody else who this would be useful for here. But here's the problem. And I wish I had the numbers that were in your problem. So I'll just do it more in symbols and generalities than actual numbers. But you had a little cart and it was on wheels, and the idea that was frictionless. But as it went back and forth because of this, well, two things. One, it's a spring connected to it, and the other one is you have a force that oscillates. That is, the force goes back and forth with time. And there is some dampening on this problem. The dampening we might call air resistance here, or maybe a little thicker. Maybe this is done underwater, and so there's a viscosity with it. But the idea is if you take Newton's second law of motion, that is, you add up all the forces and set it equal to ma, there should be three forces on this object. There is the first force, which comes from the spring, and so that's your Hooke's law, the minus kx. Then there is the viscosity of whatever fluid it's in. That's that minus c times however fast it's moving in the fluid. And then there's this, what I'll call external driven force that changes with time according to omega, and so it has a sinusoidal pattern. And so those are the three forces, and that has to equal to ma. And the idea then is to solve this for A. What is the position of it? Or in that particular problem, they say something about certain condition is met so that the amplitude is 3. And that might not even be the maximum amplitude. But let's just try to solve this. And this is really a differential equation. Usually the best way to do this is to put everything involving x on one side of the equation. So having the acceleration already on the right, I'll just write it as the second derivative so I can see it's part of x. And then taking the dampening effect, and so here's the coefficient of dampening, and then the velocity, which would be dx dt, and then the force from the spring, which is kx. I now have a differential equation that I need to solve. X is on one side, and then time factors on the other. And this was kind of our discussion that to do a complete rigorous solution of this is kind of overkill. And so like a Laplace transform is not really needed here. We can invoke the idea that perhaps, and this is where it's maybe not completely rigorous, perhaps the result is that it oscillates back and forth by some factor at some frequency. And I'll just say alpha, maybe not even assume it's the same as the driving frequency. Or perhaps maybe it has some kind of decaying exponential with it too. Here's the idea that if you put these two concepts together, you could say something like this. Let's just assume that it follows some amplitude e to the alpha t, where if you allow for complex numbers here, the imaginary part of the alpha would be an oscillating part, and a real part, or a real part that has a negative number, would be a decaying part. And so this type of function actually covers quite a few possibilities as long as it follows this form. And in fact, if you let the a out in front also be the possibility of a complex number. You could say, you know, this, well, I'll just say a, that's a complex number, can be written as the magnitude of a, e to the I phi. And so we'll take advantage of that later on, but this would be saying then that this would allow for a phase between the driving force and the response. And that covers a lot of possibilities, but not all the possibilities. So here's what we like to do in a lot of physics and engineering courses is say, well, let's say that it follows some combination of a trig function, an exponential decay, a phase that is different than the driving force. We could then say x is equal to a e to the alpha t. And like I said, if there's some other pattern, this won't work. So this is not a complete solution to the full differential equation. However, if we assume this form, we're assuming a lot of possibilities that seem reasonable. And if we get an answer, then we can say, well, yes, we have an answer. And that's what I was calling the uniqueness theorem, is that, you know, you might have an equation like 2x plus 1 equals 7. And without actually solving it, you might just, you know, try a few values of x and see if you kind of pinpoint, yeah, 1's too small, 2 too small, 3. Oh, 3 does it just right. So x equals to 3. And you didn't try every possibility. You didn't get down to the nitty-gritty of what you'd call a rigorous solution. But you did it more by an inspection. And the bottom line is you got the answer. And so if you got the answer, it doesn't really matter how you got there. You got the answer. And so that's the uniqueness theorem. So that's what I'm going to do. In fact, maybe I better label this as page 1 because I can see this getting kind of long here. But I'm going to try to then solve this differential equation by, first of all, using complex numbers, although I really only care about the real part of the complex number. But using the complex number and writing the x like this allows me to have exponential growth or decay, lets me have trig functions with a phase, so a cosine could be a sine or even somewhere in between. And so let's do that. So let's rewrite this equation. So here, let's write this as f equals e to the I omega t. And what I'm really saying is I want the real part of this, because the real part would be the cosine function. Okay. Then over here, I could put m and then the second derivative. Now, maybe it's worth writing here the first derivative and the second derivative, because the first derivative just pulls down an alpha and gives me the same function back, and the second derivative just pulls down another one. So these are eigenvectors and eigenvalues of the differential operator. And so I don't change the function, I just get the exponential term down in front. Okay, so again, just writing this equation. So this would be m, and then the second derivative would be alpha squared a e alpha t. The second term would be c, and the first derivative would be alpha a e alpha t. And the last term then would just be k. Oh, I better put page number 2. Would be a e to the alpha t. And so now you can kind of begin to see a solution come out of this. If you look at all three terms, we have an a in it. And also all three terms have an e to the alpha t. Then, of course, in here, we'd be left with the m alpha squared. Here we'd be left with c alpha, and here we'd be left with k. But, again, I'll say it's not a rigorous solution, but if this is going to work, then it must match this. And you can see that the time factors are here. So what that means is the coefficients would have to match and the time factors would have to match. Let me match up the time factors. So that means e to the I omega t would have to match e to the alpha t. Which, of course, means that alpha must be equal I omega. Yay! And that's our first conclusion, if, I'll say it again, if there's even a solution here. Both of these would have to match. But if we can get both of them to match, then we have a solution, and that's my point. And, of course, by the way, notice then that alpha is purely an imaginary number. And so coming back to this, which we still have to prove is going to work as a solution, but it has no real part here. So there won't be any exponential decay. That is, this thing, when it reaches equilibrium, is just going to keep, a steady state equilibrium at the same whatever. There might be a phase to it, and there might be a frequency. Although, and then we're also seeing that the frequency would also be the same as the driving frequency. So that is, the cart's going to go back and forth at the same frequency that we're pushing it. So it's not like we push it at one rate and the cart goes back and forth at a different rate. Again, if this is the solution's even gonna work. But that's the first two things we learned, that alpha is purely imaginary, so there's no exponential decay, and it has the same frequency as the driving force. Okay, now the second thing that has to match, if this is going to be a solution, is that F has to equal A times, and so I'll put an M, and then this alpha squared, I'll take advantage of our first part of this, would then be a minus omega squared, because I'd have a I omega, and when I square it, the square of I is the negative, okay? Oh, and maybe forgive me, this question comes from your engineering class, so it might be more appropriate to write a J, but I'm going to feel more comfortable with an I, and I'm this far into it, and that's more universal, so I'm going to put the I. Oh, I'm sorry, it did not come from your circuits class. So, so you would use an I for the square root of negative 1. We only avoid it in circuits because we like to save the I for current. So we repurpose J then to be the square root of negative 1 in a circuits class. But this is it from your dynamics class. So forget I even said that. Okay, so great. So I'm going to square that. Then here, actually, I'm going to put the K with it so that my real stuff goes together. Because right here, this then would be plus I C omega when I substitute alpha as this I omega. Okay. Again, following up some math here, I can rearrange this. I'll write the K first and then the minus M omega squared plus IC omega. Yay! And that does have a solution then. Or maybe I should write this in terms of A. This would say A equals to F over K minus M omega squared plus IC omega. And so that's great. That is a solution. Now, it's an imaginary number, but it is a solution. And so what this tells me so far is that this X, this motion of this cart, is going to follow this pattern, where the alpha is the I omega. So there is no, as I said before, no decaying exponential. It rocks back and forth omega at the same rate as the driving frequency. But now this is interesting. The A is a complex number. So the A then would say that there is some amplitude to it. But it also then, I guess I wrote it here, so I need to find its amplitude. It's also, there's going to be a phase with it. So in other words, the real part here is going to have some amplitude. and it's going to have the cosine omega t plus a phi. And so the response of the cart back and forth is to go back and forth at the same frequency, but not in phase. There's going to be some kind of phase given that this is a complex number. And I think that kind of makes sense, because if you're pushing on something back and forth, you know, if you're pushing this way and about the time you start to push the other way, the cart still has momentum that way. And so the cart's going to continue on. So you've already changed your direction of push. And then the cart's going to begin to slow down and then go back. And so the position of it is going to lag a little bit. It's going to have a phase to it. It may go back and forth at the same rate, but it doesn't go back at the same instant. I mean, as soon as you change your direction of force, you don't instantly change the direction of the position. And that's what I get by reading the math of having a complex number here. And it, like I said, probably best written this way. So let's do that. Let's write it this way. And then this will give us a deeper understanding of getting what is the amplitude of it. And then we could even get the phase, although I noticed in this problem you were not asked to find the phase delay between the changing of the direction of the force and the changing of the direction of the position. So maybe we won't go that far and find the phase. But this problem did ask about the amplitude of it. And so that's where we have to do some more math here. Okay, so got some more math here. Now, maybe I should say a little bit about complex numbers. There are two ways of writing a complex number. Let's say A is a complex number. You can write it as its magnitude and its phase. Or you can write it as I'll call it its real part and its imaginary part. A lot of times we put this on a grid since we got a real and imaginary part here. And we can say, okay, make it the real part along the x-axis and the imaginary part here. And so we could kind of think of this imaginary number here as so much real plus so much imaginary. Okay. And so that's our grid. And so writing in this form would be like Cartesian coordinates on a grid. And writing it in this form would be more like writing it in terms of a magnitude and then a phase. And this is really going to serve us better here because of the fact that that's what we want to know in this problem, the magnitude. And it would also be, if there was a part B to this problem, ask for the phase. So I do need to take this solution, which I now have for the amplitude, which is not wrong, but it's not written in any one of these forms. And I need to write it probably in one of these forms to get a best understanding. And since we're after the magnitude of it, let's write it this way. In fact, let's try to find the magnitude. Because another nice thing about complex numbers, if you take the number and you multiply by its complex conjugate. So maybe I'll write it in, how about this form? This would be the magnitude of A times e to the I phi. And then its complex conjugate would be the magnitude of A times e to the minus I phi. And the two exponentials, when we write it in the polar form, cancel off, and you get magnitude squared. And that's where I'm going to take advantage of, I'll call it complex analysis here, because here I have a complex number, and the question is, what is the amplitude? What is the magnitude of it? So I really want the magnitude, and I can get that by doing this step. All right, so that's going to be my next little goal here. Since I'm taking advantage of complex numbers, I can say that the magnitude of the amplitude squared is A times its complex conjugate. Okay, so A here is F over this K minus M omega squared. And then, what was it? Plus IC omega. Yeah. And then if I multiply it by its complex conjugate, I'll get K minus oh, I should put the m first to make it look like the other one. M omega squared, and then minus I C omega. And then across the top, I'll just get an F squared. And across the bottom, and this is how we're going to get a real number, no more imaginary ones. In fact, you could probably see that best here. If you do a complex conjugate of this, you get the minus, so you end up getting magnitude squared equals real part squared plus imaginary part squared, kind of the Pythagorean theorem that you would get here. And so that's what you see. So you're going to get this K minus M omega squared squared. So that's these two multiplied. And then the cross terms, this one and then this one of our FOIL, cancel each other off. And so now we just get these two multiplied together. And the I times I is a -1 with that negative, make a plus, and then you get your C omega squared. And of course, that's this imaginary part. And so now I can get what the problem needs, which is what is the amplitude by taking the square root. So the square root of the top is pretty easy. It's just F. And then down here, we would have a square root of K minus M omega squared plus C omega C squared. Yay! And I guess technically we're done, but let's keep going because this does not look like the form that's in your book. And it doesn't look like the form that is in many other books. It usually is written in two forms, one like your book and then one like your physics book. In fact, let me do this. Let me factor an m squared out of here, so that this would look something like this. Downstairs, we would get a K over M minus omega squared, and I'll leave that into the square root. But taking the M out of here means it's not there anymore, and then that's why I have the M over. Of course, we're taking it out of here, so it'd be an M squared, and then when I take it out of the square root, it would just be an M over there. And of course, I have to do the same thing over here, but it's kind of the same math where you can see if you take this M and you put it back in, it would become M squared. And when you distribute it, it would cancel off and you would just get the C over omega. Now, this might look a little funny, but it is kind of standard to put force over M in the top. And this kind of gets you an answer of how the amplitude is connected to the magnitude of the force per each kilogram. So you can think of this as, how much amplitude you're going to get for each kilogram of mass you have, or each unit of force. But the other thing about writing it this way that's kind of nice is K over M is what we call the natural frequency. I mean, this is the frequency you would get if I had just took a cart and there was, no external force and no dampening to it, and I just pulled it and let it go. And so it's only the spring. It would have a natural response. And that natural response would come out to be a frequency of K over M. So it's kind of nice then to, kind of remember that, and maybe over here on the side say, okay, let's call omega n, its natural response, K over M, so that you can write this then as omega squared n times omega squared. And this is a really nice way of writing the amplitude, because you can begin to see that what amplitude you get would depend on what frequency you're driving it at. You see this number down here, then, is this one in particular is connected to how close is your driving frequency to this natural frequency. Well, we call this resonance because if your driving frequency is the same as the natural frequency, this term goes to 0, and this is the biggest this function would ever get. And so given different driving frequencies you could apply at this natural frequency, right, it would then get very big. But if you were at a frequency that was a little higher or a little lower, because although it does have a minus sign here, you square it, the negative goes away, it tapers off. And it follows maybe something that looks like this. And this is why we call this resonance, because if you are driving it at a frequency near what we would call its natural response, you actually get a pretty big amplitude. If you get a driving frequency that's off a little bit, you'll still get it to shake on you, but amplitude won't be so great. And the further you get away, and it doesn't matter whether you're above or below the natural frequency, the less it shakes. And so if you have something that has a natural frequency of kind of at this rate, and you shake it like this, it really doesn't really move. You really got to be kind of pushing it kind of near and ideally at the natural frequency. And that's what, makes it resonant. Now, maybe I'll just grab your physics book, and I know this is from your dynamics class, but if you remember your physics book, and I went ahead and I opened it up to chapter 15, but in chapter 15, section 7, your author actually has this discussion. They don't actually solve the equation, because if you remember doing this a year ago with me in 123, we just said, well, the solution of it involves a more advanced differential equation that you need a little more math. Well, now you're there with a little more math. And so the author of your physics textbook said, well, this would be the amplitude. And so there it is. Now the only difference is right here, he used the dampening coefficient as a B instead of a C. But we've got exactly the same equation, although he doesn't do any of the work. But he does talk about the answer to it, and that's on the next page. He's doing a graph that I kind of did. He says, look, you can have these different shapes. This is called the Lorentzian shape, by the way. And it depends on how much friction you have. And so I drew one that has a certain amount of friction. If it had more, I guess it would shoot up like this, and it would kind of narrow on you. And that's what he's trying to show here. And it says, okay, you can have these different sizes, but there's a pattern, regardless of what the friction is, whether B, in this case, I'll call it C, is large or small, you can see that it tapers off in some way or another. And so this is the form I like. Let me go one more form, because another common form, and this is what your textbook has, is they take this amplitude and they factor out the natural frequency. So this becomes, in the top here, F over M, and then they put the natural frequency. Sometimes it's even worth putting it F over M natural frequency in the numerator. okay? Because you get kind of a nice pattern too. There's some advantages of this one. This is not all that bad of a choice. But when you factor out the natural frequency here, you get a 1 minus, and you get omega squared over the natural frequency squared, plus the other term. But let me hold off on the other term for just a second, because now you could see your plot of amplitude. And you can see then that it peaks when this is equal to 1. In other words, you could plot this in terms of what is your driving frequency compared to your natural frequency. You might call this the driving frequency in natural units. And so it's centered around this 1. And so you get some maximum value, which would be based upon the natural frequency. And then you have your Lorentzian shape tapering off, whether you're a little above or a little bit below. And so if your driving frequency is a little above the natural frequency, you're somewhere about here. If it's a little below, you're somewhere here. Now, to finish the equation, I guess if I factored out a natural frequency squared, I need a, let's see, natural frequency squared. Yeah, I got to put one in here. So it's going to be a C omega over omega n. And so there it is in the units of omega n over m squared. And so it's nice, like I said, that it's in units of omega n. Yeah, I think that's right. Now, I guess I'll stop there. Your problem then had actual numbers in it. And I think you were supposed to find out what is the value of C when your amplitude was equal to 3. And, of course, I'm not sure what the natural frequency was, because that would be your K over M. And I'm not sure what the driving frequency was for your problem. But I'm going to suspect, since it was set up to be a pretty hard problem, they deliberately made these different by a little bit. And so maybe your driving frequency is a little bit higher than your natural frequency. So maybe it's right here. And so this is supposed to be a 3. And so if you were to change your driving frequency to this natural frequency, you could get an amplitude greater than 3. Of course, there still would be a maximum. And I don't recall what the numbers are. But that's what you are designed to put in. Now, I could be wrong. If they actually gave you a driving frequency at its natural frequency, that would be great, because that means this would go away. And so now you can just set that equal to 3, and it's a much easier problem to solve because you're just taking the square root of a square. So that goes away, and then you solve for C. So if they gave you the easy one where the math has the driving frequency equal to the natural, great. If not, well, you got even more algebra to do. All right. Hope that would help. That was kind of fun to go through. Take care.